Hello and welcome back. In this lecture, we're going to continue our discussion on quadratic equations, and let's continue with question 50. For what values of m, so m is a parameter here, one root of equation 2x squared minus mx minus 1 equals 0 is minus 8 times the other root. So if we have two roots x1 and x2, let's assume that x2 is minus 8 times x1, okay? So again, in this quadratic equation, we have 1 degree of freedom on n, all right? And then because we're also assuming a relation between the two roots, this removes the 1 degree of freedom. So we end up with excuse me, 0 degree of freedoms, right? And m has to have specific values, right? Otherwise we cannot have this relation for any value of m. Okay, all right, we have two roots, and basically the ratio of the two roots, x2 over x1, is 8, right? And we can do this in different ways. We talked about the specific case that the two roots have a relation. The ratio is some constant. We talked about what is the relation between the coefficients, but I'm going to drive it again from the scratch. So from the quadratic equation, we already know that the sum of the two roots, x1 plus x2, is minus b over a, which is m over 2, and the product x1 x2 is c over a, minus 1 over 2. And then we substitute for x2 in the product. Minus 8 x1 squared is minus 1 over 2. Therefore, x1 squared is 1 over 16. Therefore, x1 can be plus minus 1 over 4, right? And therefore, x2 can be minus 8 times this, minus plus 2, right? So if x1 is plus 1 over 4, x2 is negative 2. If x1 is negative 1 over 4, x2 is plus 2. Therefore, x1 plus x2, which is m over 2, can have two possible values. Either 1 over 4 minus 2, which is minus 7 over 4, or minus 1 over 4 plus 2, which is plus 7 over 4. And therefore, m could be plus negative 7 over 2, which is the second choice. All right. Now let's look at another interesting thing about quadratic equation. Let's say, let's consider that a quadratic equation is given. Ax squared plus bx plus c equals 0 is given, okay? And our variable here is x, so x is our variable. And what we want to do is to make a new quadratic equation such that there is a specific relation between the roots of the two equations, okay? And the question is how to actually make that. What is that the other quadratic equation? Now there are two ways of doing that. We already discussed that if I know the roots, so basically the idea is that I have a quadratic equation and the variable is x, so let's call the roots x1 and x2. And then I want to create another quadratic equation that has two roots, y1 and y2. And there is a relation between these y1 and y2 and x1 and x2, right? And then the question is, what is the quadratic equation that gives me these two roots? Obviously, if I know the sum and product of the two roots, then these two new roots. Therefore, I can actually write down the equation. Let's call it the variable y, minus sy plus p equals 0, right? So if I know the roots, I can write down the quadratic equation, right? So one way is to find the roots of the first quadratic equation, and then based on the relation that we define, find the roots of the second quadratic equation, and then calculate the sum and product and find the quadratic equation that we're looking for, right? So the first method is that Name the roots of the first equation x. Basically the variable is x, the roots are x1 and x2. This is the notation we use for the roots. And the second equation y. So the roots for the second equation that we're looking for is y1 and y2. And write x in terms of y. So we know that the y has to have a relation with x, right? So basically we take our quadratic equation, the original one. Let's say I want y be, I don't know, some function of x, right? And what I do is that I write x as the inverse of this function in terms of y and plug it back here, right? So write the original quadratic equation in terms of the y. A f inverse y squared plus b f inverse y plus c equal, and then simplify this to eventually get something like a prime, some other coefficient y squared plus b prime y plus c prime equals d. Okay? Alright, question 51. Form an equation whose roots are 4 units less than the 3 times of the roots of this equation, x squared minus x minus 1 equals 0. So this is our original equation, original quadratic equation, and we want to find a quadratic equation whose roots, basically y1 and y2, are 4 units less, so 3x1 or x2 minus 4, right? So this mapping y equals 3x minus 4 should be valid, should be established between the roots of the new equation and the original equation, right? Now how do we do that? Again, the first method is to directly calculate x in terms of y in the mapping. So our mapping is y equals 3x minus 4, and therefore x is y plus 4 over 3, right? And then put this back in the original equation. Y plus 4 over 3x squared excuse me, this is x minus y plus 4 over 3, right? This is the second term, minus 1 equals 0, right? And then we basically simplify this. And if I want to simplify it, let's multiply by 9, y squared y squared plus 8y plus 16 minus 9y minus 3y. Simplify, multiply by 9, 3y minus 12 minus 9 equals 0. Okay, so the quadratic equation, the new one, is y squared plus 5y, 9 and 16 minus 12 is 4, minus 5 equals 0, right? And the name of the variable doesn't matter, so we can change it back to x squared plus 5x minus 5 equals 0. X squared plus 5x minus 5 equals 0. So the second choice. Alright? Alright, the point here is that consider this quadratic equation ax squared plus bx plus c equals 0. This is always our original terminology. And we can look at the special cases, right? So these are special cases. One is we can form a quadratic equation whose roots are the inverse of the roots of this original one. In order to do that, we choose the mapping. We write down the mapping in terms of x and y. X is the original, is the new variable, such that y is 1 over x, and then x is 1 over y. So we write down the original variable in terms of the new variable and put it back in the original quadratic equation, a 1 over y squared plus b over y plus c, and then multiply by y squared, which is c y squared plus b plus a. Now you see what happens here. So the conclusion is that if if you change the position of A and C, right? C becomes A becomes E, then the roots are inverted. The roots are inverted. It's very interesting, right? You interchange the position of A and C, the roots are inverted. And this is the easiest way to prove that. Now, if we want to form an equation, a quadratic equation whose roots have the opposite sign, right? So we define the mapping y equals negative x. X is the original variable, which gives us the original roots. Y is the new variable, which gives us the new roots. And then we write down x, the original one, in terms of the new variable, puts it back in the original equation, a minus y squared plus b minus 1 plus c equals 0. And the only thing that happens is that the b becomes negative b, right? So the coefficient of x1 just changes sign. And it's easy to see that because if y1 is negative x1, y2 is negative x2, these are the new roots, these are the old. So y1, y2 new roots, and x1, x2 are the old roots. And therefore s prime, the new s, y1 plus y2 is minus s, and p prime, which is y1, y2, is the same. And therefore the new equation is y squared minus s prime y plus p prime equals 0, which is y squared plus sy plus p equals 0. So the coefficient of y changes sign, right? The coefficient. So if I make b to negative b, I get a quadratic equation whose roots have opposite sign with the original. Now the third case is if we want to make a quadratic equation whose roots are k units more than the original one. Again, x is the original variable in the original equation, and y is the new variable, which gives us the new roots, and k is a constant, right? So we want to have this mapping, so we write the original variable in terms of the new. Basically we invert the mapping, okay? And then we put x in the in terms of y in terms of the original quadratic. So a times 1 minus y minus k squared plus b y minus k, which is again x, plus c equals 0. And then you can simplify this. A y squared plus k squared minus 2yk plus by minus bk plus c equals 0. Therefore a y squared, so the coefficient of y squared doesn't change. And then we end up with minus 2ka plus b y plus c minus bk plus ak squared equals 0, right? Something like that. So y squared one term, y has two terms, and the rest are constants, c minus bk plus ak squared. Otherwise, you don't need to remember this. You just have to remember the method, how we actually obtain this equation, right? It's very important for you to know that. Alright, and finally, the last case is we want to make an equation whose roots are k times than the original one. Again, so we define our mapping from the original variable, which gives us the original roots, to the new variable. K is our constant, and then we invert this mapping. So we write x in terms of y over k, and put it in the original equation. Y over k, a y over k squared plus by over k plus equals 0, and then we multiply by k squared. So ay squared bky plus c k squared. Okay. Now the second method, I already discussed that, but it's easy to see that if we can't use the direct approach, which means defining the mapping, right? Directly or explicitly define the mapping. If we cannot do that, we can form the sum and product for the new roots, s prime and b prime, of new roots in terms of sum and product of the old roots, s and p, right? Then we can write down the standard form of a quadratic equation. X squared minus sx plus b equals 0. When the coefficient of x squared is 1, this form is called the standard form. Standard form. And this is in general true for any polynomial. When the coefficient of the leading term of a polynomial the leading term xn, this is called the leading term xn, or the x to the highest degree is called the leading term, right? When the coefficient is 1, this is called the standard form. Form an equation whose roots are the cubes of the roots of equation of x squared minus 2x minus 1 equals 0. Now the original method is that, okay, y should be x cubed. Therefore x is y to the 1 over 3. And then we put it back, y to the 2 over 3 minus 2, y 1 over 3 minus 1 equals 0. But then here's the problem, right? This doesn't give us a polynomial. This is not a polynomial. A polynomial should only have integer powers, right? So it should be y2, y1, y0. So there's something wrong here. So this method, the defining of the mapping, doesn't work. So the way we're going to handle this, we say, okay, for the original equation, I already know if the roots are x1 and x2, I know the sum and the product, right? x1 plus x2 is minus b over a, which is 2. And the product x1, x2 is c over a is minus 1, right? Now the roots of the mapping, y1 plus y2 is x1 cubed plus x2 cubed. But this is a symmetric expression, and I know that it's equal to s cubed minus 3sp, right? So s prime, the sum of the new roots, is s cubed minus 3sp, 8 plus 6, which is 14, right? And then y1 times y2, which is p prime, the product of the new roots, is x1 cubed, x2 cubed, which is p cubed, which is minus 1. So the new equation is x squared minus s prime, which is 14, x plus p prime, which is minus 1. So the first choice. Alright, rule 1. Suppose f of x is a map, is our function, our polynomial function, quadratic function. Let's call this quadratic function. ax squared plus bx plus c equals 0. And it has two roots, x1 and x2. We want to determine the position of a given number beta with respect to x1 and x2. Okay. Let's say I don't, the thing here is that we don't want to, let's write it down. So we don't want to explicitly calculate the roots, calculate x1 and x2. We don't want to do that, but x equals beta is given, and just on the x-axis, we know that my equation has two roots, and it better has two real roots, right? Two real roots. I want to know where beta is. Could be in this interval. Let's call it number 1. So beta less than x1. x1 is the smaller roots. Or it could be between the two roots, beta in the second region, between x1 and x2. Or it could be greater than both roots, right? In the third. So first one, beta is less than the two roots. Region 2, beta is between the two roots. And region 3, beta is greater than x2 and of course x1, right? But the point here is that we don't want to explicitly calculate the roots and then compare them with with the beta. So how do we do that? It's very interesting. Basically, the idea here is that if a, the coefficient of the leading term, which is x squared, right, times f of beta, so you evaluate f of x at beta, right? If a times f of beta is negative, then beta is between the two roots. Okay, beta between the two roots. If a times f of beta, and again f of beta is evaluating the quadratic equation at beta, right? So this is f of x evaluated at beta is positive, then beta is outside the two roots. So between the two roots is region 2, which I drew up there, right here, and outside the two roots is regions. It's either region 1, which is less than both roots, or region 3, which is beta is greater than both roots. And my advice here is to prove them. And I'm going to prove it for you, but you can try it first. How do we do that? All right, so as I mentioned many times, if I write down the quadratic equation ax squared plus bx plus c, I can write it or factorize it in terms of x minus x1, x minus x2, right? This is the standard factorization based on the roots. X1 and x2 are roots, right? Now what happens, let's define g of x, x minus x1, x minus x2, right? And this is the factorization of the standard form where the coefficient of the leading term x squared is 1. And let's assume that we have two real roots, right? Eventually this quadratic equation has, let's call this g of x. Has two roots, and the shape, so if x is very large, if x goes to infinity, g of x is a very large positive number. And again, if it goes to negative infinity, it's also g of x is a large positive number. So its shape is always like this, right? It goes to plus infinity at both ends and becomes negative between the two roots, right? This is like, you just immediately can draw this. So you can see that g of beta is positive if beta is outside the two roots, right? And again, for x less than x1, let's go region 1, x between x1 and x2 region 2, x greater than x2 region 3, right? This is our notation. So g of beta is negative for region 2 and is positive for region 1 and 3, right? So if in the region 1 and 3, region 1, which is the second case, g of beta is positive, so the sign of fx is the same as the sign of a, right? So the same sign. And two real numbers have the same sign if and only if their product is positive, right? So in region 2 is the first case, right? When beta is between the two roots. And g of beta is negative, so the sign of f of x and the sign of a is different, is opposite. And it only happens when a and f of beta, the product is negative, so they have opposite sign. Okay? Alright, question 53. What is the value of m that 2 is between the two roots of equation mx squared minus 3x plus 4m minus 1 equals 0? So m is our coefficient a. Let me just write them down explicitly. M is our coefficient a, b is negative 3, and c is 4m minus 1. And our beta here is 2, right? Beta is a number, and this quadratic equation is f of x, right? And 2 is between the two roots, right? Alright, so if beta is between the two roots, therefore a times f of beta should be negative, right? And therefore m times 4m f of 2 we have to calculate. So x equal to 4m minus 6 plus 4m minus 1 should be less than 0, right? So m times 8m minus 7 should be less than 0. Again, this by itself is a quadratic equation, and it has two roots, m0 and m7 over 8. And basically the shape is something like this, and the negative happens when m is between 0 and 7 over 8. Okay, so m should be positive, so we can cross out second and third choice, and m should be less than 7 over 8, which is less than 1. Let's see if we made a mistake here. 2 is between the two roots, so m times 4m minus 6 plus 4m minus 1, 8m minus 7. So either m is no, I guess we didn't make a mistake here. Let's see, 4m minus 6 plus 4m minus 1, which is 8m minus 7, 7 over 8. It seems that none of the choices are correct here. Yeah, but the correct choice here is m between 0 and 7 over 8. Yes. All right, so rule 2, two quadratic equations ax squared plus bx plus c equals 0, and a prime x squared plus b prime x plus c prime equals 0 have the same roots if and only if one is a multiple of the other one. So basically the idea is that these two quadratic equations have the same roots if you can take one of them, multiply it by some real number, and get the other equation. That's the only case, which means the ratio between the coefficients a prime equals b over b prime equals c over c prime, right? I mean, obviously this coefficient that we multiply by the first one of the equations should not be 0, right? This is very obvious. Rule number 3, consider two equations ax squared plus bx squared plus bx plus c equals 0 and a prime x squared plus b prime x plus c prime equals 0 have only one common root. So one common root, one of the other roots is different. Have one common root. This is very interesting case. So I'm going to start it. This is interesting. We have two quadratic equations, number 1, number 2. And these ones share one root in common, so have one root in common. Let's call this root t. So t, if I take t and plug it back in both equations, it satisfies the two equations. Then plug it into both equations and eliminate the quadratic term x squared. It's very interesting. So at squared plus bt plus c must be 0 because t is the root of the first one. And the second one, a prime t squared plus b prime t plus c prime is 0. Now if we take them and take these two and put them in the standard form, remember in the standard form the coefficient of the leading term x squared is 1, right? So t squared plus b over a t plus c over a is 0, and t squared plus b prime over a prime t plus c prime over a prime is 0. And we can just eliminate t squared and conclude that b over a minus b prime over a prime t plus c over a minus c prime over a prime should be 0. Okay, so t should be, and remember c over a was p b over a minus s and so on, right? So basically we can start from the fact that t squared minus st plus p should be 0, t squared minus s prime t plus p prime equal to 0, and then subtract them. Basically s prime minus st should be p prime minus p, therefore this common root should be basically p minus p prime over s minus s prime. So this is our common root. If two quadratic equations have a common root, this root should be p minus p prime over s minus s prime. Okay, what is the value of a such that equations x squared plus 1/2 ax minus 3a equals 0 and 2x squared minus 5ax plus 6a equals 0 have just one common root? Again, we take the first one, write an s and p. S is minus b over a minus 1 over 2a, and p is c over a minus 3a. And take the second equation and write down s prime and p prime. S prime is 5 over 2a, and p prime is 3a. And this common root should be basically this common root should be s minus s prime, p minus p prime. So, or s prime minus p minus p prime, s minus s prime, right? So this common root, let's call it so t, this common root becomes p minus p prime minus 6a divided by minus 3a, which is 2, right? So this is actually interesting, that because this common root is independent of a, and then we put it back in one of the equations, right? Put it back to find a. So this common root is 2. Let's put it in the first equation. Four plus a minus 3a equals equal to 0, therefore a is 2.